Welcome to your personalized deep dive. You
Hmm.
know how sometimes it feels like there are just too many problems in the world to solve?
Yeah.
Well, it turns out even computers struggle with that. Today we're going to explore
Right.
the
What?
fascinating world of what computers can and,
Huh.
more interestingly, can't do,
Right.
all thanks to a computer science textbook in Italian.
Interesting.
It's called Fondamenti dell'informatica UNAVR, and it's fresh off the digital press,
Okay.
dated February 29th, 2024.
Fascinating, isn't it?
Yeah.
We think of computers as these limitless problem-solving machines,
Right?
but the reality is much more nuanced.
Yeah.
There are fundamental boundaries to what even the most powerful algorithms can achieve.
The text starts off with a real head-scratcher.
Yeah.
It claims there are more problems in the world than there are possible computer programs to solve them.
Wow.
It's almost like saying there's more sand on the beach than grains of rice in the world.
Right.
But how can that be true?
Well, the textbook uses a clever analogy to illustrate this concept.
Okay.
It compares all the problems out there to the set of real numbers, those endless decimals like pi,
Yeah.
while the set of possible algorithms or solutions is compared to natural numbers,
Oh.
1, 2, 3, and so on.
Okay.
Both sets are infinite, but in very different ways.
So it's not just that there are a lot of problems, it's that the types of problems
Yeah.
outnumber the tools we have to solve them.
Exactly. It's like trying to build every possible Lego creation
Yeah.
using only a handful of bricks.
Right.
You're fundamentally limited by the building blocks you have.
Oh, okay.
And in the world of computation, those building blocks are algorithms.
Okay, so we're talking about computational power, the ability of computers to tackle different types of problems.
Uh-huh.
Where do we even begin to understand this?
Well, the text starts with a basic unit of computation, the decision problem.
Okay.
These are questions with a clear yes or no answer,
All right.
the kind of things computers excel at.
Right.
To tackle these, we need a model of computation. And the textbook introduces finite state machines as a starting point.
Okay.
Imagine them as simple computers with a limited set of states and transitions between them.
I'm picturing one of those old school vending machines. You
Right.
put in your money, make a selection, and bam, your snack appears.
Right, right.
It's a simple series of states and actions based on the input.
That's a perfect example.
Okay.
And just like a vending machine can only dispense a limited number of snacks,
Uh-huh.
finite state machines can only solve a certain class of problems, what we call regular languages.
So even with these finite state machines, we're already hitting some boundaries.
Yeah,
Are there ways to bump up the computational power to handle more complex problems?
of course. The text introduces a more flexible type of finite state machine, the non-deterministic automaton.
Okay.
Instead of following a single path, these machines can explore multiple paths simultaneously.
So it's like having a choose your own adventure book, but for computers.
Yeah.
They can explore different possibilities in parallel, but how does that actually work?
Yeah,
Does the machine just flip a coin to decide which path to take?
that's a great question. And it highlights a key difference between these theoretical models and real-world computers.
Okay.
The text gets a bit technical here,
Right.
but the gist is that non-deterministic automata have this ability to make transitions without actually consuming any input.
Oh, okay.
Like the machine can pause, look around, and consider its options before taking the next step.
So it's adding a layer of complexity, some internal decision-making that
Yeah.
simple vending machine logic doesn't have.
Uh-huh.
But I'm guessing even with these upgrades, non-deterministic automata are still limited in what they can do.
You're right. Despite their fancy name and added flexibility,
Okay.
they're still bound to those regular languages.
Right.
It's like giving a more powerful engine to a car. It can go faster,
Right.
but it's still limited by the roads it can travel on.
Okay.
To tackle a different class of problems, we need a whole new type of machine.
Okay, I'm ready for the next level up.
Right. What kind of problems are we talking about now?
Right.
And what kind of computational muscle do we need to flex?
Imagine trying to understand a sentence with complex grammar,
Okay.
or write a program that can analyze another program.
Right.
These tasks involve understanding context, how different parts relate to each other.
Oh, wait.
That's where context-free languages come in.
Okay.
And to handle them, we need to step up our computational game.
This is starting to feel a lot more relevant to our daily lives.
Uh-huh.
Parsing complex information, understanding code, those are essential tasks in our digital world.
Exactly. And to tackle these challenges,
Yeah.
we need a model of computation that can handle these nested structures and dependencies.
Okay.
Think of it like trying to match parentheses in a mathematical equation,
Right.
or making sure all the tags are properly closed in a piece of HTML code.
Okay.
These tasks require more than just simple state transitions. They require memory.
Okay. So we need a computer that can remember what it's seen before.
Keep track of the context. What kind of model are we talking about now?
The text introduces the push-down automaton,
Okay.
which is basically a finite state machine with a built-in memory stack.
Okay.
Think of it like a stack of plates. You can only access the top one at a time.
Okay. Yeah.
This stack gives the automaton the power to remember information as it processes the input,
Yeah.
allowing it to handle those tricky nested structures.
So it's like adding short-term memory to the machine?
Yes.
That makes sense. I'm guessing the textbook has some clever examples to show how this memory stack works in action.
It does.
Okay.
One example involves palindromes.
Okay.
Those words or phrases that read the same backwards and forwards, like race car or madam.
Uh-huh.
The stack allows the automaton to remember the beginning of the string as it processes the end,
Okay.
checking for that crucial mirror image property.
Right.
It's a neat way to illustrate how memory enhances computational power.
So we've climbed a few rungs on the ladder of computability, from simple decision problems to the more intricate world of context-free languages,
Right.
all with increasingly sophisticated machines. Where do we go from here?
Well, now we're ready to tackle the big question.
Okay.
What are the ultimate limits of computation?
Right.
What can computers really do,
Right.
and what lies beyond their reach?
Okay.
To answer this, we need to meet the king of computation, the Turing machine.
I'm ready to meet this king.
All right.
Is it safe to say that Turing machines represent the pinnacle of computational power, capable of computing anything any computer could ever compute?
That's the prevailing belief in computer science.
Okay.
Turing machines are incredibly powerful theoretical models that form the foundation for understanding the limits of what's computable.
It seems like we're moving beyond just identifying different types of languages and machines. Are we entering a whole new realm of thinking about computability?
We are. The text introduces us to primitive recursive and partial recursive functions, which are essentially the building blocks of complex calculations.
Okay.
You might be surprised to learn that even familiar operations,
Yeah.
like addition, multiplication, and even the Fibonacci sequence, can be built up using these functions.
Yeah. So we're diving deeper into the nuts and bolts of how computers solve problems.
Right.
Not just the what.
Yeah.
This feels like a whole new level of understanding.
Right.
But the outline hints there's a twist.
Okay.
Something even these computational giants can't do.
Right.
This is where it gets really interesting, right?
You're absolutely right.
Okay.
As powerful as Turing machines are,
Yeah.
there are problems they simply can't solve.
Right.
Not just because they aren't powerful enough,
Okay.
but because these problems are inherently undecidable.
Okay.
Meaning no algorithm, no matter how sophisticated, can solve them for all possible inputs.
Wait, hold on. Are you telling me there are problems that are just impossible to solve?
You got it.
No matter how smart we get, how advanced our technology becomes, this is blowing my mind.
You're starting to grasp the truly mind-bending nature of computation.
Wow.
And to understand this, we need to explore the infamous halting problem, which will truly challenge our assumptions about what's possible in the realm of computing.
Okay, now I'm hooked. Let's dive into this halting problem and see what makes it so special, so impossible.
All right.
But first, I think we need a moment to process all of this.
Okay.
What do you say we take a little break and come back to tackle this computational beast? Sounds good. All right, let's pick up where we left off.
Okay.
That was a lot to take in.
Yeah.
We've gone from simple vending machines to the mighty Turing machine.
Right.
And this concept of undecidable problems.
Right.
Problems that no computer could ever solve.
It really challenges our perception of computers as these all-powerful problem-solving machines, doesn't it?
It does.
But that's what makes this deep dive so fascinating.
Right.
We're uncovering the boundaries of what's possible, not just in computing, but in our understanding of knowledge itself.
Before we get too philosophical, I want to understand this halting problem you mentioned.
Right.
What is it exactly, and why is it such a big deal in computer science?
Imagine you're a programmer,
Okay.
and you've written this amazing program that you think could revolutionize the world.
All right.
But there's just one problem. You're not sure if it will ever actually stop running.
So it could just keep going and going,
Right.
stuck in an endless loop,
Exactly.
never giving you the answer you're looking for.
Exactly. Now, wouldn't it be great if there was a program, a universal checker, that could analyze any program and tell you for certain whether it would eventually halt or run forever.
Right.
That would save programmers countless hours of debugging and frustration.
That sounds like a dream come true for any developer.
Uh-huh.
But you're about to tell me that such a program is impossible, right? That's the halting problem.
Precisely. As much as we'd love to have such a tool,
Right.
the halting problem demonstrates that it's fundamentally impossible to create.
Oh, wow.
There's no algorithm, no matter how clever,
Yeah.
that can solve the halting problem for all possible programs.
But how can we be so sure? How can we prove that something is impossible to solve? Doesn't that feel a bit like giving up before we've even tried?
That's the beauty of the halting problem. It's not just that we haven't found a solution yet.
Okay.
It's that we can mathematically prove that no solution can ever exist.
Right.
It leads to a logical contradiction,
Yeah.
a paradox
Okay.
that breaks the very foundation of what we assume computation can do.
Okay, now my curiosity is piqued. Can you give me an example of how this paradox works?
Mhm.
How we can prove something is impossible?
The text uses the concept of a self-contradictory program, which is a bit of a brain teaser.
Okay.
Imagine a program that analyzes itself
Right.
and does the following.
Yeah.
If it predicts, it will halt. It then intentionally enters an infinite loop.
Okay.
And if it predicts it will run forever,
Okay.
it immediately stops.
Wait, that's like a computer version of those. This statement is false paradoxes.
Right.
You create a situation where either outcome leads to a contradiction. So by trying to solve the halting problem, we've actually created a problem that can't be solved.
That's the gist of it. And this seemingly simple problem has profound implications, not just for computer science, but for our understanding of the limits of knowledge itself.
You mentioned that the halting problem is just the tip of the iceberg when it comes to undecidable problems.
Yeah.
What else lurks beneath the surface?
The text introduces the concept of undecidable languages. We've talked about regular languages and context-free languages, which are sets of strings that can be recognized by specific types of computational models.
Right.
Undecidable languages, however, are sets of strings for which no algorithm can definitively determine membership for all strings.
So it's like having a club with an entrance exam that's impossible to pass
Yeah.
or fail.
Yeah.
No matter what you do, you can't be certain whether you belong or not.
You're getting it. And what's fascinating is that these undecidable languages aren't just theoretical curiosities.
Right.
They pop up in various fields.
Okay.
For instance, in software verification, we'd love to have a program that could guarantee a piece of software is completely bug-free.
Oh man, that would be a programmer's dream come true.
Right.
No more late night debugging sessions, no more security vulnerabilities.
Unfortunately, the halting problem throws a wrench into that dream.
Oh.
Since we can't always determine whether a program will halt or run forever,
Right.
we can't be absolutely certain that it's free of bugs or unexpected behavior.
So even in this world of ever-increasing computational power,
Yeah.
we're bumping up against fundamental limits problems that even the most sophisticated algorithms can't crack.
Right.
It's both humbling and inspiring, wouldn't you say?
Absolutely. It reminds us that even with all our technological advances,
Yeah.
there are still profound questions to explore,
Okay.
intellectual frontiers to push.
Right.
The unsolvable is just as fascinating as the solvable, and perhaps even more so.
This is all incredibly fascinating, but I have to admit, it's also a bit overwhelming.
Yeah.
Are there any practical takeaways here, or is this all just theoretical, mind-bending stuff?
There are definitely practical implications.
Okay.
Understanding these limits helps us avoid wasting time and resources trying to solve problems that are inherently unsolvable.
Right.
It encourages us to focus our efforts on areas where computation can truly make a difference.
It's like knowing when to use a hammer and when to use a screwdriver.
Exactly.
You wouldn't try to hammer in a screw, would you?
Exactly. And just as there are different tools for different tasks,
Right.
there are different levels of computability.
Okay.
The text hints at something called computational complexity theory, which goes beyond just asking whether a problem is solvable or not.
So it's not just about finding an answer, it's about finding an answer efficiently.
Precisely. Computational complexity delves into how much time and resources an algorithm requires to solve a problem.
Right.
Even if a problem is technically solvable, it might take an absurdly long time to compute a solution.
Like the difference between having a map that shows you the way and actually having the time and energy to make the journey.
Yeah,
You might technically be able to walk from New York to Los Angeles,
right.
but it's probably not the most practical way to get there.
That's a great analogy. Computational complexity theory helps us understand those practical limitations,
Okay.
even when dealing with solvable problems.
Right.
It helps us choose the right tools and strategies for the job.
So we've gone from simple vending machines to the mighty Turing machine, from the
Hmm.
solvable to the unsolvable,
Hmm.
and now we're talking about the efficiency of algorithms.
Right.
Where does this all lead?
Right.
What's the bigger picture here?
The bigger picture is that the world of computation is a vast and fascinating landscape
Right.
full of possibilities and limitations.
Okay.
We're starting to see how these different concepts connect,
Yeah.
how they form a hierarchy of power and complexity.
It's like we're piecing together a map of the computational universe with different regions representing different levels of computability and efficiency. And even though we've encountered these undecidable areas, it feels like we've only just scratched the surface.
Yeah.
What other mysteries remain to be explored? We've uncovered some fascinating insights about the world of computation, from those basic building blocks of algorithms to the mind-boggling concept of unsolvable problems. And now I'm wondering,
Yeah.
where do we go from here? Is there more to uncover, or have we reached the very edge of what's knowable in the realm of computing?
That's the beauty of it, isn't it? Even when we encounter those seemingly impenetrable barriers like the halting problem,
Right.
it just fuels our curiosity to explore further. You know, it's like we've reached the edge of a map,
Uh-huh.
and now we're eager to see what lies beyond the horizon.
Thinking about it,
Okay.
all these different types of computational problems, the machines designed to tackle them, it feels almost like an ecosystem, a complex web of interconnected ideas.
That's a great way to visualize it. The text hints at this interconnectedness by introducing the concept of a hierarchy of computational models.
Okay.
It's not just a linear progression from simple machines to more complex ones.
Right.
It's more like a family tree, with each generation inheriting the capabilities and limitations of its predecessors.
So it's like a branching structure, a hierarchy of power and limitations.
Exactly.
That means some models are inherently more capable than others, right?
Exactly. Finite state machines, which we talked about earlier,
Right.
are a subset of push-down automata,
Okay.
which in turn are a subset of Turing machines.
All right.
And within each level of this hierarchy, there are problems that can be solved and problems that remain undecidable.
So it's like a family tree of computation.
Yeah.
With each generation inheriting the capabilities and limitations of its predecessors,
Right.
but also branching out into new unexplored territories. Some branches lead to solutions, while others lead to dead ends, those undecidable problems that defy algorithmic solutions.
I love it, that way of thinking about it.
Yeah.
And this hierarchy helps us appreciate the richness and complexity of the computational world.
Right.
It's not just about finding answers. It's about understanding the nature of the questions themselves, their inherent complexity, and the tools we have to approach them.
Okay, so Turing machines, the kings of computation, are at the top of this hierarchy.
Right.
They're incredibly powerful. But even they operate within a defined set of rules, a framework of logic and symbols. Does that mean they're the ultimate limit? Could there be other, even more powerful models of computation that we haven't even imagined yet?
Now you're asking the really big questions.
Yeah.
It's a tantalizing thought, isn't it?
It is.
The Turing machine has held its ground as the gold standard for decades.
Right.
But there are always those who wonder if there might be something beyond a computational paradigm that could crack those currently unsolvable problems.
It's like those old maps with "Here be dragons" written on the unexplored edges. There's always a sense of wonder, of the unknown lurking just beyond the boundaries of our current knowledge.
Right.
Perhaps somewhere out there, there's a computational dragon waiting to be discovered.
And that sense of wonder is what drives scientific inquiry, the pursuit of knowledge. Those unanswered questions, those unsolved mysteries, they're the fuel for our intellectual engines.
This entire deep dive has been a journey of discovery, hasn't it?
It has.
We've gone from simple decision problems to the intricate dance of context-free languages and the mind-bending world of the halting problem. It's been both humbling and inspiring to realize that even with all our ingenuity, there are fundamental limits to what we can compute.
It's been a fascinating exploration, hasn't it?
It has.
A blend of power and limitations, of what we can achieve and what remains forever beyond our grasp.
Yeah.
And through it all, we've gained a deeper appreciation for the complexities and wonders of the computational world.
Well, listener, we've reached the end of our deep dive.
Mm-hmm.
We've journeyed from the basic building blocks of algorithms to the very edges of what's computable.
Right.
Hopefully, you've gained a new perspective on the power and the limitations of computation,
Uh-huh.
the questions that drive us,
Yeah.
and mysteries that still beckon.
Remember, even though we've encountered problems that are demonstrably impossible to solve,
Right.
that doesn't mean we should stop exploring.
Okay.
Every question, solvable or not,
Yeah.
is an invitation to think deeper,
Mhm.
to push the boundaries of our understanding.
So stay curious, keep questioning, and who knows, maybe you'll be the one to uncover the next breakthrough,
Yeah.
to chart a new course through the computational landscape.